Every quantum computer ever built has a fatal secret. Not a software problem, not a math problem, a plumbing problem. Thousands of fragile wires running from room temperature electronics down into a chamber colder than deep space. Every wire leaks heat. Every degree of heat destroys quantum information. And the more qubits you add, the more wires you need, until the whole system drowns in its own thermal noise. For 2 decades, this wiring bottleneck has been the single greatest obstacle standing between us and a useful quantum computer. The kind that could simulate new drugs in hours, or crack every encryption algorithm protecting your bank account, your medical records, and $600 billion in cryptocurrency. On February 26, 2026, a team at Fermilab and MIT Lincoln Laboratory announced they'd solved it. They engineered ultra-cold control chips that sit inside the cryogenic vacuum itself, right next to the quantum processor, eliminating the massive wire bundles entirely. One compact chip replacing thousands of cables. The thermal bottleneck that made million-qubit machines a physical impossibility? Gone. Physicists called it an exciting new direction. Intelligence agencies called it terrifying. Because the exact same hardware that will simulate life-saving molecules can also run Shor's algorithm. And Shor's algorithm breaks encryption. All of it. Google has already revised its Q-day estimate, the day a quantum computer cracks modern encryption, to 2029. The global cost to retrofit every digital system on Earth against that threat? $1 trillion. And as of March 31, 2026, Google researchers proved they could crack Bitcoin's encryption in 9 minutes using fewer than 500,000 physical qubits. The clock isn't ticking, it's already moving. The wiring bottleneck. To understand what Fermilab and MIT actually achieved, you need to understand the engineering nightmare they inherited. A quantum computer's processor has to operate at 4 Kelvin, negative 452 degrees Fahrenheit, colder than outer space. At that temperature, atoms barely move, electrical resistance vanishes, and quantum states can survive long enough to perform calculations. But the electronics that control those qubits, signal generators, voltage regulators, readout amplifiers, operate at room temperature, 300 Kelvin, connected to the quantum chip by thousands of physical wires, each one a highway for heat. And heat is the enemy of quantum coherence. At 50 qubits, you can manage the wiring. At 100, it's a serious engineering challenge. At 1,000, the thermal load from the cables alone overwhelms the refrigerator's cooling capacity. The system physically cannot stay cold enough to maintain quantum states. Every major quantum platform, superconducting circuits from Google and IBM, trapped ions from IonQ and Quantinuum, Microsoft's topological approach, has slammed into the same wall. The qubits themselves keep improving. The infrastructure to control them cannot scale. The entire quantum computing industry has spent 20 years making better qubits, while ignoring the fact that the wires connecting them to the outside world were the real bottleneck. Until February 2026. What Fermilab and MIT built. The collaboration drew from 2 of the most powerful physics institutions in the country. Fermilab, the Department of Energy's flagship particle physics laboratory, and MIT Lincoln Laboratory, a federally funded research center with decades of precision electronics experience for defense and intelligence applications. Their target was trapped ion quantum computers, systems where individual charged atoms are suspended in electromagnetic fields and manipulated with lasers and voltage pulses. Trapped ions hold the record for qubit quality, gate fidelities above 99.9%, coherence times measured in minutes, but their Achilles heel has always been control infrastructure. Scaling to tens of thousands of qubits means tens of thousands of electrodes, each fed by its own heat-leaking cable. What the Fermilab team did was engineer specialized, ultra-low-power cryoelectronic control circuits capable of operating at 4 Kelvin. Not room temperature, not even an intermediate cooling stage. Directly inside the cryogenic vacuum, mounted millimeters from the ion trap itself. MIT Lincoln Laboratory provided the ion trap platform, a precision-machined chip with arrays of microfabricated electrodes designed to hold and shuttle individual ions. Fermilab's cryogenic circuits plugged directly into this platform, replacing the massive cable bundles with a compact, integrated control system. The proof of principle results were definitive. The cryoelectronics successfully moved individual ions, held them at precise set positions, and drastically reduced the thermal noise that had plagued every previous scaling attempt. One compact chip doing the work of thousands of cables, without melting the quantum states it was supposed to protect. The project was backed by two of the DOE's most prestigious quantum programs, the Quantum Science Center and the Quantum Systems Accelerator. This wasn't a startup pitch deck. This was the United States government betting its quantum future on killing the wiring bottleneck at its source. And the implications ripple far beyond trapped ions. Superconducting systems from Google and IBM face the same thermal scaling wall. So does Microsoft's topological approach. Any architecture that needs to communicate between a cryogenic chip and room temperature control hardware hits the same limit. And Fermilab just demonstrated a way through it. What still has to happen? Now, before anyone prints the victory banner, there are real engineering hurdles left to clear. The current cryo-electronic circuits can hold voltage set points for milliseconds. Useful quantum computations require those voltages to remain stable for minutes or even hours. That's a gap of several orders of magnitude. The transistors behave differently at 4 Kelvin than at room temperature. Threshold voltages shift, leakage currents change, and every component has to be recharacterized from scratch. But the architecture itself, the fundamental idea of putting control electronics inside the refrigerator instead of outside it, has been validated. The thermal barrier has been breached. The design is explicitly built to scale to arrays of tens of thousands of electrodes, enabling direct connectivity to tens of thousands of qubits without a single room temperature wire touching the quantum chip. That's the breakthrough. Not a better qubit, not a better algorithm, a better way to control a million of them at once. Why intelligence agencies are terrified. Here's where the story turns. Because every advance in quantum hardware scalability is simultaneously an advance toward breaking encryption. Every secure website, every banking transaction, every military communication on Earth relies on RSA 2048 or elliptic curve cryptography. Systems built on math problems that take classical computers trillions of years. A quantum computer running Shor's algorithm doesn't need trillions of years. It needs hours. In 2019, cracking RSA 2048 was estimated to require 20 million physical qubits. By May 2025, Google's Craig Gidney proved algorithmic optimizations could slash that to fewer than 1 million physical qubits and just 1,399 logical qubits, a 20-fold reduction. Then, on March 31, 2026, Google researchers demonstrated that Bitcoin's 256-bit encryption could be broken in 9 minutes using fewer than 500,000 physical qubits. Over $600 billion in digital assets exposed. An independent group called Oratomic showed neutral atom hardware could achieve the same result with as few as 10,000 qubits, targeting the 6.9 million Bitcoin sitting in dormant wallets with exposed public keys. Google has officially revised Q-Day, the moment a cryptographically relevant quantum computer goes live, to 2029. Harvest now, decrypt later. But the scariest part isn't the future, it's the present. Intelligence agencies around the world, China, Russia, Iran, North Korea, the NSA, GCHQ, are running a strategy called Harvest Now, Decrypt Later. They're intercepting encrypted data right now and stockpiling it. The moment a quantum computer cracks Shor's algorithm at scale, every byte becomes readable. As Boston Consulting Group warned, data stolen today will be compromised in the 2030s. Starting migration in 2030 will already be too late. NIST finalized its post-quantum cryptography standards on August 13, 2024, 3 new algorithms designed to resist quantum attacks. The UK's National Cybersecurity Centre has urged every organization to complete migration by 2035, calling it a transition more complex than fixing the millennium bug. The estimated global cost of that migration? $1 trillion. The global quantum arms race. The Fermilab and MIT breakthrough doesn't exist in isolation. It lands in the middle of the most aggressive hardware arms race in scientific history. Google's Willow chip, 105 qubits, 99.97% gate fidelity, nearly 10 billion error correction cycles without failure. IBM targets the Starling system by 2029 with roughly 200 logical qubits using codes that cut physical overhead tenfold. Microsoft's Majorana 1 promises topological qubits with even greater overhead reduction, targeting 1 million qubits on one chip. China is spending an estimated $15 billion. Their Zhuchangji 3.0 matches Google at 105 qubits. Their 12,000-kilometer quantum communication network is the largest on Earth. The U.S. counters with the CHIPS and Science Act, $278 billion authorized across federal agencies. The EU has launched a €1 billion quantum flagship. The UK has pledged £2.5 billion, and the commercial stakes are staggering. McKinsey estimates quantum computing could unlock $200 to $500 billion in pharmaceutical value by 2035, because quantum computers simulate molecular interactions natively, bypassing every approximation classical supercomputers are forced to make. The Fermilab MIT cryoelectronics breakthrough doesn't just help one qubit modality. It removes a fundamental thermal constraint that applies to every platform attempting to scale. It is the engineering key that turns theoretical roadmaps into physical reality. What this means for you. So where does this leave you? If you have cryptocurrency in a wallet with an exposed public key and 6.9 million Bitcoin due, the window to migrate is shrinking. If your company stores sensitive data encrypted with RSA or ECC, nation-states may already have a copy. If you work in healthcare, finance, defense, or energy, every system you touch runs on encryption with an expiration date now measured in years. The Fermilab MIT breakthrough solved the biggest obstacle to million-qubit machines. Google, IBM, Microsoft, and China are all racing to build them, and fewer than 500,000 physical qubits can break the encryption protecting $600 billion in digital assets in under 9 minutes. The question isn't whether quantum computers will break encryption. The published research has already answered that. The question is whether the world can complete a trillion-dollar cryptographic overhaul before the machines are ready. And right now, with cryo-electronic control chips sitting inside vacuum chambers at 4 Kelvin, moving ions with precision no cable bundle could ever match, the machines just got a whole lot closer.